This is the second video about equilibrium. How exciting. What I'd like you to do to begin with is think back to that first video. We said that we had to have two things in place for a reaction to be in the state of dynamic equilibrium. One of those was to do with rate, and one of those things was to do with concentration. Have a think, pause the video. What are the two things which need to be in place for a reaction to be described as being in dynamic equilibrium? We said the rate of the forward and the reverse reactions must be the same. The forward reaction and the reverse reaction must equal each other. And we also said that the concentration of the reactants stays constant over time, and that the concentration of the products stays constant over time. Those two things might not be the same as each other, that would be unusual, but the concentrations of each of the reactants and the products will remain constant over time. That's what we mean by dynamic equilibrium. Now, what I'm interested in is what happens to the position of equilibrium if I change something. We're going to start by looking at, let's change the concentration of one of the reactants. Let's increase the concentration of a reactant. Let's go back to this idea of the equilibrium constant Kc, because this, if you understand this, this is the way in to understand why changing the concentration of a reactant, for example, will change the position of equilibrium. At equilibrium, we've said that these things stay constant and this stuff stays constant in terms of concentration. So that means the concentration of products stays the same and the concentration of reactants stays the same. Which means that when you know the values of these things, you can end up with a numerical value for Kc. And that is, as the name suggests, a constant. It doesn't change. So whatever you do to this reaction, we have to have a constant Kc value. Now just think about that. If the value of Kc is constant, it means that this ratio, the concentration of the products divided by the concentration of the reactants, is always the same. So if you come along and add, let's add some B. If you add some B, you've disrupted this lovely ratio. You've made the bottom numbers bigger. Well, if you do that, that's going to change this sum. And the consequence of that, having a bigger bottom, would be that Kc will become smaller. And that can't happen because we know Kc is a constant. So what has to happen? Well, the ratio has to remain constant. So if you add some extra B, we need that B number to go down. And the only way it can go down is by reacting with some extra A to make some more C. So we've put more B in, this number's got bigger, but we need this to stay the same. So the B has to react with some more of the A to make more of the C. So the moment you've added the B, you've disrupted the equilibrium. And it has to change. And it has to change in order to keep Kc constant. I have to bring back this equilibrium, this ratio, to the original value. So by adding more of this reactant, it's going to react with more of this, so that these numbers will now go down after that addition, and this number goes back up in order to go back to the original ratio. The numbers of A, B and C will all be slightly different, but the ratio will be the same. I hope that makes sense. So let's think about our notes. Increasing the concentration of reaction. Increasing the concentration of a reactant will cause what to happen? Well, the Kc ultimately has to be the same, so the position of equilibrium has to change. This extra B that I've added, we've got to get rid of it. We've got to get rid of it somehow. And the only way we can do that is by making it react with some of the A to turn into more C. So we end up with more C at the end. The ratio stays the same, but we've ended up with more C as a consequence of adding more B. So the position of equilibrium has moved in this direction. That's how we phrase it. Because we've ended up with more of this, the position of equilibrium has moved to the right-hand side, or it's moved towards the products, or in favour of the products. Okay? So increasing the concentration of reactant will cause the position of equilibrium to change. And it will move in favour of the products. Now, some guy called Le Chatelier observed this process. And he observed that whatever you try to do to a reaction, the system, the equilibrium, does the opposite. You add reactants, what's the consequence? The concentration of reactants goes down and the concentration of products goes up. The system is doing the opposite of what you have just done. Now, the subtle way to think about this is what I've been trying to introduce you to. Think about Kc. Kc is a constant. If you do something like make B bigger, in order to re-establish Kc to its original value, I need to make more of this, and the total of this needs to come down in order to re-establish the original ratio. That might sound technical, but it's going to help you understand things at a higher level when we get to year 13. Okay. Let's think about pressure. This is one of the things that you covered at GCSE. What happens when you increase the pressure on the position of equilibrium? Now I'm going to go back to my Haber process equilibrium. The equilibrium between nitrogen and hydrogen and NH3, ammonia. Let's get that balanced up. What I'd like to do is think, what will be the Kc? What will be the expression for Kc for this reaction? Pause the video, have a go at trying to write the expression for Kc. Okay. We said that Kc is equal to the concentration of products divided by the concentration of reactants. What about these numbers? Because what we're really saying is 1 lot of nitrogen reacts with 3 lots of hydrogen to make 2 lots of ammonia. We have to take these numbers into account. What I should really be writing is this, because I have to think about all of the products and all of the reactants. Now I could simplify that. Nobody ever writes it like this. I've got ammonia concentration times ammonia concentration on the top. So whatever that whatever that number is, that is the power that I'm going to use. I've got 1 lot of nitrogen on the bottom. I have got 3 concentration terms for hydrogen, all times together, so I'm going to cube that. So Kc is going to equal this particular expression, in this case. Okay. So let's think about our equilibrium then. Nitrogen plus hydrogen is turning into ammonia. If I increase the pressure, what would Le Chatelier say? What's going to happen to the position of equilibrium if I increase pressure? Well, Le Chatelier said, if you remember, although you don't actually need to memorise his idea, you just need to know the idea, what it is, don't need to be able to regurgitate that in an exam. Le Chatelier said, whatever you do, the system, the equilibrium, is going to do the opposite. So I'm going to increase the pressure. So the system has to try and do the opposite. It has to decrease the pressure. How does it do that? Well, I can see I've got lots of reactants, lots of concentration terms for the reactants, and fewer concentration terms for the products. So let's imagine this whiteboard is a sealed container, and I've got some nitrogen and some hydrogen in any random kind of orientation. Now what's going to happen when I start to change my equilibrium? Will you imagine this sealed container with all these gas molecules whizzing around? Pressure is to do with how often those molecules collide effectively into the side of the container. So you increase the pressure. The system has to decrease the pressure. How can it do that? Well, it can do that by making fewer molecules inside. So you've increased the pressure, perhaps by making the chamber smaller. That would increase the pressure of the reaction. How does the reaction respond? Well, it needs to move the position of equilibrium to reduce the pressure. How can it do that? Well, if you think about that balanced equation, if I take a nitrogen and react it with 3 hydrogens, I get 1 ammonia. I've got fewer molecules in there, so the pressure has gone down. So if I increase the pressure, the position of equilibrium is going to move to the side of the reaction where there are the fewest moles. In this case, increasing the pressure will make nitrogen and 3 lots of hydrogen react together to make 2 ammonias. I forgot one of them. There are fewer molecules when that happens, and so the pressure goes down. So what's the general rule of thumb here? What do I do? Well, when I look at my equation, I can see I've got on this side, there are 4 lots of moles, and on this side, there are 2 lots of moles. So all I have to do is identify which side has the fewest number of moles on, increase in pressure. All I'm going to do is move the position of equilibrium to the side with the fewest moles. This will go up, this will come down. Okay? So, changing the pressure only affects the position of equilibrium when I've got this closed system. Increasing the total pressure will cause the position of equilibrium to move to the side with the fewest moles. Now temperature. Let's think about again what Le Chatelier would say for temperature. Increasing temperature is going to have 2 impacts. One of those impacts has nothing to do with equilibrium, and the other one does. The first impact about changing temperature is it makes reactions faster. And the second impact is it will change the position of equilibrium. And we need to separate out those 2 ideas in our heads and hold them clearly independent of each other. There is an impact when you change temperature on rate of reaction, and there is a different and unrelated impact on position of equilibrium. Now, here's the interesting thing. What happens to the position of equilibrium when you change temperature will be different depending on whether a reaction is exothermic or endothermic. First of all, what's the sign? What's the sign for an exothermic reaction? And what's the sign for an endothermic reaction? Excellent. I'm sure you got that right. Exothermic reactions, the sign is negative. Delta H is negative. And for an endothermic reaction, delta H is positive. Okay, if the temperature is raised and the forward reaction is exothermic, let's go back to our lovely ammonia equilibrium. What's going to happen? Well, what we're saying is, what do we mean when we're saying this reaction is exothermic? Let's say delta H equals negative exo. That means the forward reaction, when you see this sign next to a reaction telling you it's negative, that's talking about the forward reaction. So in this case, what we're saying is the forward reaction is exothermic. That means the reverse reaction is the opposite, endothermic. Well, that obviously makes sense when you think about it. An exothermic reaction, delta H, is negative. The reverse reaction, delta H, would have to be positive if I was going in that direction. Let's think about this Le Chatelier guy. What did he say would happen? Well, if you increase the temperature, you're making the stuff hotter. What's going to happen? Well, the system, the equilibrium, has to do the opposite. If you're putting heat energy in, the system has to take heat energy out. And it can only do that by absorbing energy. And it can do that by going in the endothermic direction. So the moment that you increase temperature for an exothermic reaction, the endothermic direction will be favoured. And the position of equilibrium will move in the endothermic direction, which in this case is towards the left-hand side. So for this example, be clear, for this example, where the forward reaction is exothermic, when you increase temperature, the endothermic direction is favoured and the position of equilibrium will move in the endothermic direction, which in this case is in the reverse direction. And the position of equilibrium moves towards the left-hand side. Now, what's going to happen if you use a catalyst? Well, again, let's think about what we mean by a catalyst. A catalyst, we know there are two types of catalyst, heterogeneous and homogeneous. A heterogeneous catalyst is one which is in a different state to the reactants. A homogeneous catalyst is one which is in the same state. Now, it doesn't matter whether we're talking about heterogeneous or homogeneous catalysts. A catalyst basically changes the rate of reaction. It provides an alternative pathway with a lower activation energy. So catalysts tend to make reactions faster. What do they do to equilibria? Nothing. They don't alter the position of equilibrium. They just enable you to get to that point faster, but they don't actually change the equilibrium position at all.